Now the cosine similarly, remember the original cosine started at the top. So this one starts at the top, just also stretched by a factor of absolute value of A. It goes through here, down to the bottom, and back to the top once, top all the way down back to the top from 0 to 2 pi over b, it's new period. And this is y equals a cosine dx. The stretching factor in the vertical direction makes it go between plus and minus the amplitude. Stretching factor in the horizontal direction makes this new period 2 pi over b instead of 2 pi. And so you can sketch either one of those that way. And now we want to just review a couple of those things. For an example, suppose I wanted to sketch. And then also, I guess I should say, if this one's flipped upside down, then you turn it upside down and it goes like this, right? So you just flip it in here and it, that's if A is negative, it looks like that. All right, so suppose I wanted to sketch y equals minus 2 sine of 1/3 x. What does that do for me? Instead of figuring the stretching factors that like I do in algebra, figuring out a whole bunch of points, I just immediately write the amplitude is absolute value of A, the absolute value of minus 2 is plus 2. The period is 2 pi over b, 2 pi over 1/3. You have to be careful with your quotients here, right? You might say, oh, that's 2/3 pi. No, it's not. You rewrite it as 2 pi over 1 over 3. Top times, right, you take the top times the reciprocal of the bottom, which is also top times bottom, over middle times middle, and they say, oh, that's 6 pi. They reinforce each other, right? So I draw the same way with period 6 pi and amplitude 2. And this is a flipped cosine, flipped sine, excuse me, since A is negative. Now the sine always starts at the origin, so I draw it through the origin in any case. And now I just have to draw the guidelines up here, and absolute value of A is 2. And minus absolute value of A is y equals minus 2. And I start at the origin, and I just, instead of going up and back, down into the middle, since it's flipped, I go down and back up into the middle. And it looks just like that. And then it has to have a period of 6 pi, so this will be 6 pi here. And this is the graph that we want. It goes between plus and minus 2 now. It's stretched twice as tall. And it repeats once every 6 pi because it's stretched 3 times as long in the x direction. Then the wave goes on forever, it never ends, so you can draw some arrows going off. This is one period. If I ask you to sketch 2 periods, that means you just do this again and go out another 6 pi to 12 pi. Now here's 2 periods if I ask you to draw that. But one thing about this, just for your science classes, that I didn't see in my math classes, so I like to tell people, if you take your garden hose out in the backyard and give it a jerk like that, and this bump runs down here and runs across the grass, that's a traveling wave. They call it, that's a traveling pulse is what they call it. So a wave is actually something that repeats over and over. If you shake it up and down, up and down, up and down, ignoring friction, it could go like this. A wave is something that repeats over and over like that. It doesn't have to be a sine wave, but if it's a sine function that repeats over and over forever, then you call it a sine wave. So a wave is something that repeats forever, where this single bump is a pulse. Just for science purposes, we'll ask you that on the test. Now the object today, let's review there with a little different example. How about what else is someone in science going to do with these? This makes a nice thing. You can make them go up and down real fast by changing the period. So you have a high frequency wave, like representing a high pitch in the sound something. And you can make it go real high up and down. That can make a strong earthquake or a weak one, a loud sound or a weak one, right, when you're doing vibration analysis. But we haven't moved it over. What if the water is up here and you want a wave up here in the water? Or something like that. Or maybe you don't want it to start at the origin or at the top or bottom. You want to have this shifted over. Maybe you're not starting the wave at t equals 0, but you're starting the wave at t equals 1 or something. What can you do to shift it? In algebra, there's a technique for shifting too. we're going to call it translation. The graph of y equals f of x minus a is the graph of y equals f of x shifted, translated, proper term really, a units in x. Right if a is positive, left is if a is negative. That's whatever's subtracted here is the shift. Can you think why that is? Like if I put, here's y equals x squared, right? What is the graph of y equals x minus 1 squared, right? If this is your f of x, the rule, function is a rule, you give it x, it gives you back exactly one number or whatever kind of thing it gives back. What does y equals x minus 1 squared look like? This is that function where you replace x with parentheses, put in x minus 1. This is f of x minus 1, right? What does that look like? Well, x has to be 1 greater to square the same number, right? If I put in 0 here, I get y equals 0. But if I put in y equals 1, x equals 1 here, then I square 0 and get 0. So it's going to be here. And over here, I have to put in x 1 greater to square the same number and get the same y value. So it's actually the same parabola, exactly the same shape, moved over 1 unit. This one, if you put in 1, you get 1 squared is 1. This one, you have to put in 2 to square 1. So it's got the point 2, 1, right? And instead of having minus 1, 1, right? You get minus 1 here, you put in x equals 0, so you get 0, 1. And so this is exactly the same shape as that shifted over 1 unit. That's a horizontal translation in x by a units. If you replace x by x minus a, it just moves the parabola over a units. That's true for any function, no matter what function it is. And if you take y equals f of x plus b, what does that do to your original graph? Oops, that's wrong. F of x plus b on the outside. That just adds b to every y coordinate, right? It's y equals f of x shifted b units vertically, right? Because it adds b to every y coordinate. If y is negative, it can go down. Now what you can do is put the two of those together and shift anywhere you want in the plane, right? So y equals f of x minus a plus b shifts or translate each point on the graph. Well, it keeps the same shape function, just like the parabola there. A units in x horizontally, b units in y vertically. Right? We can do that with our trig functions now. Hence, if I take y equals a sine b times x minus little a, all plus little b, that does it, right? I took the graph. This moves or translates y equals a sine dx, the thing we've just been graphing, it was just stretched by a units horizontally and also by b units vertically. Now I'm going to change this around a little bit. Instead of little b here, like we use in algebra sometimes, let's call this d. We can just give it a different letter. Now the shift is d units vertically. That's the book. That's what the book uses, and a lot of trig books use that letter. And we can multiply this out in here. We can write this as y equals a sine bx minus BA plus D. And we can call this letter C. And we notice that, right, all I did is multiply out, so the shift is still A. But now, if we let C equal BA, then A equals C over B is the shift, right? A is still the shift because I replaced X by X minus A. But A is, if I let A be C over B, then the shift is C over B horizontally. And what we've deduced is that if I write these letters, Y equals A sine BX minus C, I'm calling this C, plus D, is the graph we already did, Y equals A sine BX. That was the stretched one. Shifted or translated B over C units in X. We call it a phase shift. If it's a horizontal shift, they'll call it, for waves, the horizontal shift is called a phase shift. And D units in Y vertically. That's the one we want, right there. But the idea is to show by algebra that that's actually what happens, and that's what we take Y equals A sine BX, we replace X by X minus A, that makes a shift in A units, which is also C over B, and A equals C over B, and then we put a plus D on the end, that's the vertical shift, because you add a number at the end of any function, and it just moves it vertically by that amount. Similarly, obviously, Y equals A cosine BX minus C plus D translates the graph we just did, that just had stretches in it, A cosine BX by C over B horizontally and D vertically. Now we've got it. Not only can we make it as tall as we want and as compressed or stretched as we want, we can move it around wherever we want. And this encompasses all things we call sine waves. So the sine function we call the sine wave, because it's sine, right? Cosine wave, we also call it sine wave because it's the sine wave just shifted over pi over 2 nits to the left. Same shape, we'll still call it a sine wave. Now, if we're just going to stretch them and move them, we'll still call them sine waves. And so all these things boil down to this. What we've shown then is that Y equals A sine BX minus C plus D. Some books put plus C here, they prefer that form. You'll see some differences in notation here. I'll stick with our book. Y equals A cosine BX minus C plus D. Can be sketched as follows, right? It's really just the algebra techniques you already learned. You can already sketch these if you think about it using your algebra techniques, right? What we've come up with is a faster way to do it. When you write this down, you can figure how it comes from the sine and cosine, rewrite it in that form that we just showed. But the easiest thing to do is say we can sketch it by one, computing the amplitude. The vertical stretching factor is always absolute value of A. Right? That was our stretch. To encompass the horizontal stretch, we compute the period and just make one wave over one period, takes into account the horizontal stretch or shrink. And the period is 2 pi over b, rather than trying to figure out, multiply the whole thing by 1 over b. Again, this assumes b is greater than 0. If b is less than 0, you also have to flip horizontally. We're going to avoid that because we can. So I think the book bothers to put 2 pi over absolute value of b for that reason. So amplitude, period, what we call the phase shift is a term they use with waves when it's a horizontal shift. So the phase shift is the horizontal shift in a periodic function, like a wave. So the phase shift is then going to be c over b. That's what we showed. That's the horizontal shift. And the vertical shift, we'll just call it that, is b. And then there's a flip upside down if a is negative. Also flip horizontally if b is negative, but we're not going to do that normally. And what happens is whenever you see one of these functions, you can figure out what the 4 letters are by looking at it. And then you compute these 5 properties and you sketch it. That takes into account all the shifting and stretching from algebra in a fast way. Okay. Here's what I recommend to do first. I've never seen a book do this real well for me. Even when I was trying to teach this stuff, trying to follow the book sometimes is a little awkward. Because here's what happens. There's actually only one point that shifts by the phase shift and vertical shift. What point is that when you shift the graph? Only the origin, actually, right? Because what you're doing when you take any graph and you do these shifts and stretches is the origin shifts by that amount, and then you stretch it horizontally and vertical, and every other point then moves again except the origin, right? Because you're doing a vertical stretch about the x-axis, a horizontal stretch about the y-axis. Everything gets stretched after the initial shift by the amplitude a and by 1 over b, the stretch factor in the y direction. So what I like to do is find the shift point. I'd like to start with these, move the origin in the original graph, and then think of shifting everything around it. So to sketch, we can, I'll start with these. I think that's the easy way to do it. We find what I call the shift point. The book doesn't use that term, I don't think. C over b, d, where the origin moves to, right? That's the horizontal shift and the vertical shift. And from there, we sketch y equals a sine bx minus c plus d, a general sine wave. That's the original sine function, just stretched it and shifted. From there, by sketching the guidelines where the peaks and valleys touch, plus or minus a units, well, let's say absolute value of a units above and below the guideline, the shift point. So you go to the shift point, go up and down a absolute value of a units, sketch those horizontal guidelines. That takes into account the vertical stretch. Put the wave through the shift point for a sine, not for cosine. Headed up through there if it's not flipped, but if you flipped it upside down, it should go down through there, right? Up for a bigger than 0, upward, let's say. Initially upward, or downward for a less than 0. So it's upside down. Going up and down between the guidelines, completing write that down, up and down between the guidelines. Completing one period in 2 pi over b units. That's it. All right. Let's try a simple example here. It now has a stretch like last time, but also a shift. Suppose I said sketch y equals 2 sine 3x minus pi over 4 plus 1. What does that look like? The first thing to recognize is that it is an a sine bx minus c plus d, right? So what I do is whatever multiplies the sine function, I call a. Whatever multiplies x, I call b, and I check that it's positive. Whatever's subtracted here, not added, but subtracted is c. And whatever's added out here is d. Well, I pick off the 4 letters visually, and then I compute these 4 things, right? 5 things, excuse me. I compute the amplitude absolute value of A is absolute value of 2 is 2 in this case, right? The period is 2 pi over B is 2 pi over 3, right? The phase shift is C over B, so it's whatever subtracted here plus pi over 4, right? Over B, which was 3. And you do these quotients carefully, right? You might say, oh, it's pi over 12, right? No, it's not, right? Yes, it is. I'm sorry. You might say it's 3 pi over 4. You rewrite it as a quotient of quotients just until you're used to it. Pi over 4 over 3 over 1. Top times bottom is pi. Over middle times middle is 4 times 3. These actually reinforce each other. You get pi over 12 is the phase shift. So it's phase shift of pi over 12, period of 2 pi over 3, amplitude of 2. The vertical shift d is whatever's added on the end is 1. And then flip upside down, no, A is positive. Now I can sketch it just as easy as can be. Following my prescription here, I first find the shift point where the origin of the original graph sine moves to, right? Here's the original sine. The original sine goes through the origin, goes between plus and minus 1, completing a period in 2 pi, right? So that's y equals sine x, and its guidelines are plus and minus 1. And the idea is here, where the started through the origin, I'm now going to put at the shift point, which is the phase shift pi over 12 and the vertical shift 1. So I'm going to find pi over 12, that's about a quarter, right? And 1, and put it right here. Pi over 12, 1 is C over B, D. Now from there, I go up and down absolute value of A units. So A is equal to 2. I go up 2 units to 3. And I draw the line y equals 3. I go down 2 units, 0 minus 1. And I draw the line y equals minus 1. Those are my guidelines. I'm going to make a wave that goes up and down between those. There's no flip. So I start with it going up through the shift point like that, just like the natural sine does. So the origin comes to come over here. I go up through it just like I went through the origin since I didn't flip it. Then I go up to the top guideline, down to the bottom guideline, and back to the midline. Don't have to draw the midline or the guidelines, but I think they're real helpful. Completing one period, one whole cycle of the sine wave here. After how long? 2 pi over 3. So this point right here has to be the initial phase shift, pi over 12, plus the period, 2 pi over 3. That's where that is. That's what you do. And then there it is, a whole one period exactly of this sine function. I just start at the shift point, go up to the top guideline, down to the bottom on each absolute value of A units from the middle, finishing at this initial point plus the period. Right? And then it actually goes on forever. So here's one period, and I'll draw the arrows out after that. Moreover, what I'd like you to do on the test is get 5 exact points. This is what your calculator can't do. Your calculator has a graphing feature on there, and I encourage you actually to check your answers on there and make sure it looks right. But it won't generally give you these exact points unless you just pick a really easy function. But what happens is, remember, just like this one crossed halfway in between a pi, this one will cross its midline halfway in between. So if this is pi over 12, let's see what this one is. We got to put them over a common denominator, right? It's pi over 12 plus 8 pi over 12 is 9 pi over 12, right? So if it goes from pi over 12 to 9 pi over 12, what's halfway in between? It's 5 pi over 12, right? Halfway between 1 and 9 is 5. So 1 pi over 12, 9 pi over 12, halfway in between is 5 pi over 12. What's halfway between 1 pi and 5 pi? It's 3 pi over 12. And some of these simplify, right? 3 pi over 12 is pi over 4. And halfway between 5 pi over 12 and 9 pi over 12, this one is 7 pi over 12. So now I can get this point exactly. It's 7 pi over 12. So your calculator won't tell you pi, right? 7 pi over 12, and at the bottom guideline, minus 1. I get that point exactly. This point here is at 5 pi over 12 and on the midline, so it's 5 pi over 12, 1. This point here, which was the shift point, we already wrote it. This one here is at 3 pi over 12 and the top guideline, so 3 pi over 12, 3. And we call that pi over 4, 3. There it is, 5 exact points. 3 of them on the midline and then a peak and a valley point. When you do that, that's why I sometimes ask for the test. And you check them on your calculator to make sure they look right. We'll have to do calculator problems probably next time. But let's see how that takes into account all that algebra stretching and shifting. You just compute these 5 things from the 4 letters, and you've got it, right? Let's try one more. I'll get rid of this. Suppose this time I want to sketch y equals minus a half cosine pi over 4x minus pi over 3 plus 1. Just like the sine, I first pick off A. A can be negative. A is what multiplies the sine or cosine. B is what multiplies x. C is what's subtracted from bx, not what's added. D is what's added at the end. There's the 4 letters A, B, C, D. I can figure the 5 properties from the 4 letters, right? And I say, what's the amplitude? That tells me how far up and down are the guidelines from the middle. Is absolute value of A is a half. The period is always 2 pi over B. You just have to memorize these 5 properties, but they're not hard actually, right? This is the hardest one, probably 2 pi over B. Let's see, it's 2 pi over pi over 4. And again, you do these quotients carefully. Once you're used to them, you can do them fast, just be careful. But you notice when this B has a pi in it, the pi's are going to cancel. I'm going to take top times bottom is 8 pi over middle times middle is pi. And the pi's cancel, I just get 8. No pi in it anymore. So if B has a pi in it, then you can get units without pi in it. This will just repeat every 8 units. 3, let's compute the phase shift or horizontal shift. Is always C over B. Well, what is that? That's plus pi over 3, what's subtracted here, divided by pi over 4. Since these both have a pi in it, they're going to cancel. I'm going to get 4 top times bottom, 4 pi over middle times middle, 3 pi. And the phase shift is just 4/3. So it moves over horizontally 4/3 units and then repeats every 8 units, going up and down half a unit from the midline. Now the vertical shift is whatever's added on the end, D. 1. And finally, this one is flipped, because A is negative. I can sketch that, it's not very hard. So it takes into account all the algebra techniques in an easy way. I'll first find the shift point. Looks like to put these two first, I think, because they do the stretching before the shifting. But really, again, only the origin is shifted. So you move the origin to here, and then you stretch in these two directions afterwards, I think is the easiest way. So I'm going to find the shift point is 4/3, 1. So here's 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4/3 will be about here, somewhere in here, and vertical shift is 1. So 1. Let's scale it differently. Let's put 1 here, and so here's the point. 4/3, 1. The shift point, I call it, the phase shift and the vertical shift. That's where the origin moved to from the original cosine. Well, the original cosine looks like this, right? It starts top and repeats after 2 pi units, going up and down between plus and minus 1. This was y equals cosine x. And so I'm imagining in my mind when doing these things to it, first thing I'm going to do is say, well, this was the origin that corresponds to this point. The cosine starts at the top, so it doesn't start here. The amplitude is 1/2, so here's 2. I might, and here's 3/2 right here. I might start here if it was an unflipped cosine, but it's a flipped cosine. So I'm gonna actually start at the bottom guideline. I'll draw the shift point, then I'll draw the guidelines, 1/2 unit above and below this shift point. The midline goes through the shift point always. Point that out. Then here's a guideline. Absolute value of A units above it is 1/2 unit above is y equals 3/2. Then absolute value of A units below at y equals 1/2. I've got another guideline. And the flipped cosine starts at the bottom, right below the shift point. All right, but you're imagining flipping this upside down and then shifting the origin over here. Flipped cosine is start at the bottom guideline below the shift point. Okay. And now what I have to do is draw a wave that has period 8. So I go over here 8 units from the shift point coordinate 4/3 to this point way out here, 8 4/3, which would be about right here. So this point here is the 4/3, the initial beginning of the wave, plus the period. Well, let's see, this is 24/3 and 4/3 is 28/3. 9 is 27/3, that's right, 9 1/3 here, about where I drew it. And what I do is I have it finish the wave at the same point it started. So if the cosine starts here, straight below the shift point, its starting point must be 4/3, the phase shift, and the bottom guideline, 1/2. I want to finish also at 1/2, but way out here at 28/3, 28/3 for x. So it's 28/3. 28/3, 1/2, where it finishes. Right? And what you do for a cosine is you start at the bottom or top, depending on whether it's flipped or not flipped. Go up to the top and back down to the bottom, completing one wave. just touching the top guideline and the bottom guideline. And then you get 5 exact points. This one you have exactly because it's on the bottom guideline, but still below the shift point. We already figured that. This one you have exactly because we added one period to the x coordinate and kept the y coordinate the same. What's this one here at the top? Well, it's halfway between these. You can average your x coordinates. You can say, well, what's 4/3 plus 28/3 over 2, for instance? 4/3 plus 28/3 over 2 gives you the point halfway between. Well, let's say it's 32/3 over 2 is 32 sixths or 16/3. If you add those and divide by 2, do a lot of fractions. Those nice calculators I told you about, they take a longer learning curve, but they will do your fractions for you exactly if you buy one of those. But this point is at 16/3, just the average of the beginning and ending x coordinates. And it's on the top guideline, so I know immediately that its coordinates are 16/3, 3/2. There's that one. And then these two in between are on the midline, so they're going to have y coordinate 1. And what's the x coordinates halfway between these? So you average 4/3 and 16/3. Right, what's halfway between 4 and 16 is 10, so this is going to be 10/3. It's halfway between 4/3 and 16/3. And halfway between 16/3 and 28/3 is 22/3. So this is going to be 22/3. 1. Even those are nasty fractions. You just do halfway and halfway and halfway, and you can figure them out. You can average the coordinates. I just like to say halfway between 4/3 and 10/3, right? Halfway between 4 and 10 is 6, so this is 6/3. Anyway, oops, I'm sorry, it was this one. Halfway between 4/3 and 16/3 is 10/3. There's 5 exact points and a nice cosine graph. Okay. Can you do those? I'm going to ask that on the next exam, not this one. There's a whole bunch of problems on that in the homework. And then, hope this is still up here. I had it up at the beginning. There it is. If you can figure the graph from the equation, why can't you figure the equation from the graph? And you can, given that this is a sine wave, and then it looks as it is. It's all, you can't always be sure. Assuming it looks as the truth is, and it's actually a sine wave, you can figure its equation. How can I figure the equation for this one? You just need to go in the reverse order. What you need is a shift point to start with, and the shift point has to be on the midline. Right? So the midline looks like it's y equals -3, assuming that's right. We can make this the shift point, and it would be an upward sign going through there. Or we can make this the shift point of -3 and 2 and -3, and it would be a flipped sign going down through there. Or we can make the shift point right here, and the shift point has to be in the midline. Call it a cosine that starts up here, or we can make the shift point here and call it a cosine that's flipped upside down. Let's not do that one. That's complicated. The easiest one for this one is to pick this point here, because then I don't even have a horizontal shift. It's just a vertical shift down to here, and then an upward sign. I don't have it flipped. I don't have a horizontal shift. It's nice, right? So I can pick any one of these shift points where the sine wave crosses its midline. Any one works, or where it has a peak above it or a valley below it. Any point on the midline that does that can be a shift point. Just whether you want a right side up sign, upside down sign, right side up cosine or upside down cosine. And there's an infinite number of answers on this one. That's where I lose out. I have to figure out whether your answer is right from an infinite list of correct answers. All right, so let's do that example. I'll try and recreate that sketch a little bit. Find the equation for the sine wave, which you can use either sine or cosine, and there's an infinite number of shift points you can use on either. And here it is, hopefully. -1, 2, 3, 4, 5. And it goes right through here. And it looks like here's 1, 2, 3, 4. So these are actually equally scaled. And it looks like it goes up to here, down to here, down to here. And if you draw the guidelines, that you can see it goes up and down between -1 and -5. And here's the midline, if you like that one, going through these points. Now, from the 5 properties, find the 4 letters. A, B, C, D. And then I'll have the equation. And I have a choice of using sine or cosine. If I want to choose this shift point, the easy one, I always make it easier, less likely to make a mistake that way, right? I try and do 2 things at once and blow it. Anyway, I can't even rub my stomach and pat my head sometimes. You ever tried that before? It's amazing. Anyway, brain halves get confused. But shift point, even though one half of the brain controls the left hand, the other half controls the right hand, right? And the left brain controls the right hand normally, the right brain controls the left hand. It's very strange. Shift point, then if I'll choose the shift point, I can choose anything on the midline that corresponds to a minimum, a maximum, or a crossing of the midline. Choose the shift point. 0 minus 3 for simplicity means that I have a right side up sine wave. The easiest case, sine function, I should call it, not just a sine wave, that includes cosine, but sine function, because it goes through that point. Now, I look and see the amplitude in here. Since it goes up 2 units from there and down 2 units from there, evidently 2 is the amplitude, which is also the absolute value of A, but it's unflipped, so that's actually equal to A. So I just got A equals 2. Right? From looking at how high it goes up and down, it goes up 2 units, down 2 units. A must be plus or minus 2. It's unflipped because it's coming up through the shift point. So we say A is plus 2. Now, how about the period? We notice it starts here at 0 and goes all the way to the top to the bottom, back to the middle in 4 units. So 4 is the period. But the period is always 2 pi over b. So I deduce immediately by reciprocals that 1/4 is b over 2 pi. Multiply by 2 pi, and I got b equals pi over 2. There's b. Now I look at the phase shift. The phase shift is 0, right? Because it's the horizontal shift. 0. Choosing this shift point, the phase shift is 0. If I choose this one, the phase shift is 2. If I choose this one, the phase shift is 3, etc. So 0 is the phase shift I chose. Has to be C over B. I already have B, so I can always compute it, but in this case, it's even easier. If a quotient is 0, that means the numerator is 0. So C equals 0. And then D is the vertical component of the shift. The vertical component of the shift is -3. It's vertical shift. Is D. I have A, B, C, D, and I know it's an upright sine function, so I write immediately y equals A sine bx minus c plus d. D always subtracted, D always added is 2 sine pi over 2 x minus 0 plus -3. There it is. There's the exact equation. And then we prefer to write these as simply as possible. So rewrite it as y equals 2 sine pi over 2x. Forget the -0. And instead of plus or -3, just write -3. There we go. Certainly don't leave it as minus a minus something, right? So that's a little clearer. There's the graph that should come out that way. Run on your calculator and check, see if it looks like that, right? Good with that one? Okay, so we can find a graph from an equation. We can find an equation from a graph. What else can we do? Sometimes these graphs are kind of nice for solving trig equations visually. Really, to solve them exactly, you prefer the unit circle, but there's a few problems on that here. So let me write these out. Example, for the basic sine function, f of x equals sine x. This is number 3 on the homework. A, on the interval 0 to 2 pi, square bracket here, round bracket here, solve f of x equals 0. And again, from algebra, you have to remember what this means. What does this interval notation mean? When the square bracket is there, it means include that point. When the round bracket is there, it means don't include it. So I mean, this interval, x greater than or equal to 0, but strictly less than 2 pi, not equal to 2 pi. How can I solve f of x equals 0? You can do it on the unit circle, actually, and we're going to do that more in the future. But sometimes you just think, well, the graph looks like this, y equals sine x. I know it's graph. And it goes out here to 2 pi, and it crosses at pi halfway in between, and it goes up to 1 and down to -1. And so the question is, where is it equal? Where is the sine function equal to 0, right? What that's asking. Well, that's saying where is the y coordinate 0? There's 1 point here, 1 point here, 1 point here. So when it's an easy number like 0, you can say, oh, I know where that is. That's 0, x equals 0, x equals pi, and x equals 2 pi. But wait a minute, 2 pi isn't in the interval, so I just say 0 and pi. Right? Then B gets a little harder. Sometimes you want to also employ the unit circle. But as I said, on the same interval, 0 to 2 pi, solve f of x equals a half. That is sine x equals a half. And you can kind of get a feel for this by looking at the graph. Is the idea. Here's the line y equals a half, halfway between here and here. And you're asking, what are the x coordinates of these intersection points right here, where y, the sine of x, is equal to a half? What could those be? Well, on this one, after you figure out, well, there should be 2 of them between 0 and pi, you can look at the unit circle and figure it out. But on the unit circle, I'll use theta instead of x and say I'm solving sine theta equals a half, and that'll be my x here. What angle theta has sine the y coordinate equal to a half? Well, the y coordinate is the sine on the unit circle, so I'm asking what angles correspond to those 2 points on the unit circle? Well, there's a terminal ray here and a terminal ray here. There's only 2 terminal rays. And if theta is restricted to be between 0 and 2 pi, 1 revolution, then there's only 2 angles also. Theta here and theta here. What could those be? Right? And here's what you do, what we were doing before, right? You drop the perpendicular and say if the y coordinate here is a half, then this side of the triangle is 1/2. Look at the reference triangle. And then this is 1 because it's a unit circle. If this is 1 and this side is 1/2, you know you can use the Pythagorean theorem to solve the last side, right? It's square root this squared minus this squared. But you already know the triangle that has these 2 sides. If you use the Pythagorean theorem, you get square root 3/2, right? This one we memorized. 1/2 square root 3/2, 1. And similarly, if you drop the perpendicular here, it also goes down a half. The radius is 1, and so this side is also square root 3/2. What triangle has sides 1/2 square root 3/2, 1? It's the 30, 60, 90. So this is 30 degrees, also known as pi/6. We'll do all these in radians in this section. That's what's useful in applications. And if that's 30 degrees, then by symmetry, this is also 30 degrees, pi/6 radians. Now I know what theta is, right? Doesn't leave enough room here for it though. And this one, theta is pi over 6. And this one, theta is pi for a straight angle, back up pi over 6. So pi minus pi over 6. Well, it's 6 pi over 6 minus pi over 6, getting a common denominator. Leave 6 pi minus pi is 5 pi all over 6. There it is. So two angles only, pi over 6 and 5 pi over 6 are the answers. And you can get them by kind of thinking in your head and using the unit circle here. Really, you just need the unit circle. But that graph is kind of nice to imagine it ahead of time and have an anticipation of what to get. Helps keeps you from making bad mistakes, large mistakes. All right. These are not as important. Those are the important problems, the ones that are most likely to get on the test, but there are these homeworks, and I might put them on the test to sort of see if you're an A student or a B student. But you'll pass the test without being able to do these. These are sort of conceptual problems that come up in science and so forth a lot. One of the following functions graph the function and verbalize how the graph varies. Let's say verbalize your sketch. What if I gave you the graph of g of x equals x plus sine x? This is the kind of thing sometimes you see in later courses. So this is not what you need to know to pass trigonometry. It's what you might use from trigonometry at a later date. Can I sketch that? And these things come up in practice, actually. What you do is you break it up into two pieces. Look at the graph y equals x. Oops, there's a line through the origin that splits the axes, right? Remember how to do this from algebra? Y equals x can also be thought of as y equals 1 times x plus 0, right? It's y equals mx plus b. So m, the slope is 1, and b, the y-intercept is 0. It has to have slope 1 and go through y equals 0. So here's the y-intercept 0. And if you go over 1, it goes up 1. So it splits the axes. Y equals x, as I said, is all the points for y and x coordinates are equal, or slope 1 and y-intercept 0 tells you how to graph these things in general. Now, so that's that line. But whenever you see y equals a number times x plus a number, it's a straight line, right? It's the mx plus b form. And then I also have the graph of y equals sine x. Well, that starts with the origin. And 1, 2, 3, like that. At pi, it's completed one period, so it's looking like this. And here's 2 pi out here somewhere. So this crosses just after 3.14 approximately. Well, how do I add those together? What you can do is stack their y coordinates on top of them. And the idea is that where the sine function is equal to 0, oh boy, I didn't leave enough room. It's another thing I know I'm going to teach you out of this course is how to plan ahead. This Berenstain-Bears lesson. You ever read Berenstain-Bears when you're a kid? Papa Bears always teaching you something. This is what you should not do. He tries his bicycle and crashes and says, don't do that. So I'll do here today. At x equals pi, the y coordinate here is 0. So when I add it to this y coordinate, I land on this y coordinate. So again, at 2 pi, this one's 0. And what happens is I go up to 1 unit above this thing, kind of like this, and then down to 1 unit below it, and I just draw it like that. I make it weave around this thing up to 1 unit above when you're at this point here, pi over 2. This should be 1 unit above. And at 3 pi over 2, you should be 1 unit below. Call that minus 1 if you want. And it looks like that. And so if you want to, there's the sketch, and it goes on forever, just wiggling around here, right? And you say the graph wiggles up and down 1 unit from the line y equals x, splitting the axis. That splits the axes. Okay, so there's a verbalization. I don't know what is in the answer set in the back, or even if it has one on that problem, but that's write anything like that. And it could, but that's what you can do is you can take this y coordinate, kind of stack it on top, this y coordinate, stack it on top, 0 and stack it on top, and just think of adding all these little y coordinates here onto the y coordinates of the other one. And there's a part B. That was A. This one comes up if you take a physics class in the phenomenon of resonance, where you have a signal that builds and builds and builds. H of x equals x times sine x. How can I sketch the sine function times a simple function? What you can do for this one, and this is what people do actually a lot in their math classes too. This is to give you a feel for it. Sometimes this kind of mathematical maturity helps you greatly in your later classes. A lot of our higher classes will say, well, these are the prerequisites and we want some mathematical maturity because it's a really hard class. So you get little things like this come in. How can I sketch this graph that's a product of functions? What you do is you graph the y equals x function, which again is the easy line that splits the axes. What happens if I multiply that by sine x? We notice that the sine x wiggles back and forth between plus and minus 1, right? So what we can do is think of sketching the line y equals minus 1 times x, that is y equals minus x, and the graph that their product ought to wiggle back and forth between these two lines, where if sine is equal to 1, you get x. If sine equals minus 1, you get minus x. And what's more, I'll scale this a little differently than that one. Say this is 2 pi, it completes one wiggle in 2 pi units. Here's pi. And so the sine function is going between plus and minus 1. Oops. Like that. But when you multiply it, what you get is that when the sine is 1, you're on this curve. When the sine is minus 1, you're on this curve. And in between, when it's 0, you're at 0. So it's here and here, it's equal to 0. And so you wiggle up, never going above this line because sine is never as big as 1. And so you come kind of like this. Go through 0 here, down to here, go through 0 here. And it looks like that. It just goes up and down. This is a phenomenon that occurs if you have a vibration that's reinforced, like you're pushing your little kid brother or sister on the swing. Right? Everybody likes to push them a little too hard, probably. And if there was no friction in the swing and they came back every time you push them from the same place, they go higher and higher. If you push them at random, sometimes you speed them up, sometimes you slow them down. But resonance is when you keep pushing right at the same time every time, so they go higher and higher and higher until they go over the top, right? And that's what this happens. The swing goes higher between plus and minus positions. But that happens in circuits and other things in practice. I just do the swing as sort of a physical example we've all seen. All right, so there's the last problems on there. Try those homework problems, but first study for the test. Do this for Thursday of next week before we meet again, because what we're going to do is the other graphs, the graphs of the other force trig functions, right? Oh, and I should give you the homework on that. Again, this is not due till after the test, but just do all 7 problems. The first 6 problems on there. 6.1, 1 through 6, after the test. Okay.